Good morning, everyone. My name is Kayu, a PhD student from Texas A&M, and I'm mainly focused on the shale gas development in our research group. So today I'm going to share one of the recent work, which is about water recovery ratio of shale gas wells and its effect on the shale gas development design. Here, I may explain our work by following this outline. So the first thing is the hydraulic fracturing water cycle. We know that unconventional shale gas production has been largely improved, and the main reason behind is the successful implementation of hydraulic fracturing technology. However, there are risk concerns associated with the shale revolution, especially the impacts on water resources near the shale sites. In this regard, this water cycle is developed by EPA, and 5 stages are defined based on the distinct water-related activities. Specifically, in water acquisition, groundwater or surface water is withdrawn to make hydraulic fracturing fluids. This actually could be a problem, especially in times or areas of low water availability. In chemical mixing, the obtained water is mixed with propellant and additives to create hydraulic fracturing fluids, which are then injected down into the targeted rock formations during the well injection stage. After hydraulic fracturing, water that returns to the surface is collected and handled, which is later transported for further disposal and reuse, as shown in the last stage. Generally, we have multiple options for wastewater management, such as the disposal through underground injection, the treatment followed by reuse in other fracking processes, or discharge to surface waters, and some other above-ground disposal practices like evaporation. However, finding the appropriate wastewater management strategy itself could also be a huge challenge. Here's a diagram for shale gas supply chain taken from Ann's paper. As shown, this part is the water network, and it is actually the hydraulic fracturing water cycle described in the previous slide. Note that the generally considered management practices may involve the use of on-site treatment facilities, the disposal wells, and the centralized treatment wastewater treatment facilities. The associated transportation system may also need to be considered, such as the trunk and pipeline shown here. On the other hand, the shale gas network is also required. Generally, the produced shale gas is transported to processing plants. There, the separated natural gas liquids can be directly sold in the market, while the separated natural gas, which meets the requirement, can be transported finally to the power plants for electricity generation. For example, with all these considerations, it creates many research opportunities to incorporate process system engineering approaches to address the challenges associated with supply chain management, strategic planning, and scheduling. Due to the integrated water and shale gas network, not only the usually considered shale gas production and water usage, but also the associated wastewater production should be taken into account as necessary input parameters for the design of shale gas development. One important point here is that instead of directly discussing the water use volume and the corresponding wastewater production volume, we focus on the water recovery ratio in this work, which is defined as shown here. Note that the water recovery ratio should be a function of time. Considering that the wastewater production volume can be affected by the water usage and the geological characteristics where the well is drilled, we use the water recovery ratio as a metric to characterize the wells drilled in different regions, and also serve as an important reference to predict the wastewater volume with the given volume of injected fluid for a specific well. Since the used well data can decisively determine the optimal design and the configuration of the shale gas supply chain network, we first did some preliminary data analysis on water recovery ratio data. Here, since our target shale formations are Eagle Ford and Masas, the data for flowback and produced water, as well as the shale gas production since 2009 were collected from the Drilling Info database and the Pennsylvania Department website, respectively. And the frac focus database shown here was used to collect water use data. To integrate the well data from different sources, we used the API number, which can be used for well identification, to match the water use and LP water production data for each reporting well. After the data cleaning, where we checked and removed the duplicates and unmeaningful values, those listing information for each specific well were obtained, and the water recovery ratio data were calculated. For the subsequent analysis, the latitude, longitude, and the production period data were also used. The production period here is actually the production history and thus can be obtained based on the production start and production end dates. After the processing explained in the previous slide, there were around 4,000 wells left in the Eagle Ford region, which are unevenly distributed on the map. As shown, more wells were drilled in the Webb and Dimmitt County in the southwest and the Cairns County in the northeast. Similarly, in the Masters Shale region in Pennsylvania, the wells are also unevenly distributed. And here are the numbers of the wells drilled among the 32 counties in Pennsylvania. For those collected wells, their water recovery ratios are presented here. Since most of the wells have the production period more than 1 year, and thus most of the water recovery ratios may not change significantly with the length of the production period. Here we only showed water recovery ratios calculated based on the entire production history. In other words, for a specific well, there should be only one data point on the map, in the figure. Here, the two figures on the top are for the wells drilled in the Eagle Ford region. They have the same y-axis as the water recovery ratio, but different x-axis. The two figures at the bottom are, of course, for the wells drilled in Masters region. They show that water recovery ratios are different between the two shale regions. Statistically, in the Eagle Ford region, 30% of the collected wells have the water recovery ratio greater than 1. However, in the Masters region, only 1% of the collected wells have the water recovery ratio greater than 1, and 75% of them have the ratio less than 0.3. It demonstrates that there is possibility that the cumulative IP water production volume can be greater than the injected water volume. In this sense, we can conclude that more formation brine or produced water can be generated along with shale gas in the Eagle Ford region than the Masters region. On the other hand, we may observe some data points which could be the potential outliers. For example, the red circles represent the wells with the water recovery ratio greater than 10. And the reason could be the extremely small water use volume or the relatively large cumulative IP water production volume. Also, there are some extremely low water recovery ratios due to the small cumulative IP water production volume, which could be a result of a short production history. Here, the left figure includes the associated box plots, which shows the highly right-screwed distribution of the water recovery ratios in the two shale regions. To make it clear, the y-axis is changed on the right figure and the associated statistical characteristics are provided. Since the median line of the Eagle Ford box plot lies outside the entire Masters box plot, statistically speaking, there is likely to be a difference in water recovery ratio between the two shale regions. Besides, based on the box plots, those data points that lie outside the whiskers can be viewed as outliers, and thus were discarded before conducting the subsequent data analysis. The water recovery ratio data also show there is significant variation within each shale region. Take the Eagle Ford region as an example. This figure shows that using the similar water use volume, there can be significantly different IP water production volume, which should be due to the different geological characteristics mentioned before. If looking at those data points and keeping only the wells drilled in 2013, we can get two wells in Dimmitt County which have the similar production volumes, and one well in Webb County and one well in Dimmitt County. They demonstrate that the wells drilled in different counties have largely different production profiles and thus the different resulting water recovery ratios. Even though the Webb County is actually next to the Dimmitt County on the map. So in this regard, we classified water recovery ratio data with respect to county and made the histogram for each data set. This figure shows the obvious right-screwed distribution of water recovery ratio data in each county in the Eagle Ford region. Similar phenomenon can be observed in the Masters region. So here we use median value rather than mean value to compare the water recovery ratio between different counties. Here are the calculated median water recovery ratios of the counties in the target two shale regions. By comparison, the water recovery ratios of the wells drilled in most parts of the Masters region are less than ones in the Eagle Ford region. To demonstrate how the observed variation in water recovery ratio may affect shale gas development design, a shale gas supply chain network optimization model from the literature was implemented to address the planning and scheduling problem. As shown here, the power plant is assumed as the only end user, and those numbers on the map are the numbers of the available facilities for the considered units. Note that except the transportation system between the units and the processing plants, the others are already existing. The objective of this model is to maximize the overall profit, and for demonstration, we consider 2 case studies in the Masters region, where the only differences are the well input data. Particularly, we chose the wells with the water recovery ratio around 0.1 and 0.4 in case 1 and case 2 respectively. In case 1, the simulation results show that most of the wells are drilled in shale site 2, and pipeline is always chosen for freshwater transportation due to the capacity. Since the water recovery ratio is low, the IP water volume is also low, which can be transported using trunk and handled using only 1 nearby CWT facilities. On the other hand, one large processing plant is chosen for shale gas processing, and one underground reservoir is used to store the surplus natural gas production before they are sent to the power plants later. Using this fracking schedule and the network configuration, the demand for natural gas liquids and the natural gas in the 2 power plants can be always satisfied except the first quarter, which makes sense. However, we can observe the different schedule as well as the network configuration in case 2. First, it shows that the choice of freshwater sources is determined directly by the water availability and the water demand. Second, when the IP water volume is large, like the IP water production from the shale site 1, in this case, it is economically preferred to use deep well injection due to the low injection cost, even though they have to be transported far away in the case of Masters region. Third, the on-site treatment facility using advanced technology is used here, since it is enough to handle all the generated IP water from shale site 3 and save the money from not establishing the entire transportation system. Based on this figure, the natural gas liquids demand is satisfied in the first quarter, but not in the middle of the planning horizon. This is due to the different schedule considered and the assumed lowest natural gas liquids composition in shale site 1. On the other hand, this also demonstrates that necessity of the well drill in shale site 3, which is used to satisfy the product's demands in the last quarter. So by comparison, the water-related costs accounted for only nearly 10% of the total cost in both cases. Thus, it makes sense that the overall profits are really close. This also proves that it is mainly the shale gas production profile as well as the market prices and demands determine the optimal schedule of hydraulic fracturing operations. However, we may highlight the huge difference in water-related costs due to the different water recovery ratio. Specifically, the total freshwater cost in case 1 is 54% higher than one in case 2. However, the associated total wastewater management cost is 59% lower. To conclude, so in this work, we collected the water recovery ratio data and presents its variation between the 2 shale regions, among the counties in each shale region, and also within each county. Also, we demonstrate that the different water recovery ratio may affect the shale gas supply chain network configuration, especially the water network. In the future, we may focus on how the water recovery ratio may be affected by the detailed geological characteristics, such as the permeability, porosity, and water saturation. Also, not only the water quantity, the water quality should also be considered, such as the TDS concentration or some other important caching concentrations. At the end, the results also show the huge potential to utilize distributed system design framework for the large-scale shale gas supply chain network design. So here I want to conclude, and I'm happy to take any questions.